Good day. I hope you are all well. Today we will be looking at quadric surfaces, which is more fundamental for calculus 3, engineering mathematics. Let's get going. So let's just start with a brief basic introduction. Basic introduction of what quadric surfaces are all about. Introduction, right? I just want to point out to you that every time we are dealing with a concept in maths, we need to define that particular concept. So let's understand what we mean by quadric surfaces. What we mean. So you need to understand that quadric surfaces are those type of surfaces, right, of second degree, right, of second degree of the form x, y, z, right, in three-dimensional space. Two-dimensional space, right? This is just a basic definition of quadric surfaces, right? Quadric surfaces are those type of surfaces of second degree form x, y, z in three-dimensional space, right? So let's get going. So we'll be looking at 6 common ones that I will present to you in the following slides. So let's start with the first one, which is known as your ellipsoid, right? You need to understand that the standard form of an ellipsoid, this is the standard form of an ellipsoid, right, is x squared over a squared plus y squared over b squared plus z squared over c squared equals to 1, where your a, b, c are constants, where your a, b, and c are what? Are constants. This is just a brief fundamental understanding, right? This is just the standard form of it. And you need to understand a couple of things here. You need to understand that when we do a horizontal trace, right, of this particular surface, which is your ellipsoid, when we do the horizontal trace, right, where we are saying a z must be equals to a particular constant p, you need to notice that you are going to obtain an ellipse there, right? Let's try it. Let's just try it. X squared over a squared plus y squared over b squared plus p squared over c squared equals to 1. Notice that this is a constant, right? We can put a constant on the other side, so you're going to have this as the form of an equation, right? And you realize that this is a standard form of an ellipse. That's why we are saying a horizontal trace of this is basically giving us an ellipse, right? This is just a basic understanding, as well as when you check for your vertical trace, which is y, right? You realize that you're gonna obtain the same result because you'll be putting y as a constant q here, and you realize that you're gonna have this on the left hand side, and when you transpose, you're gonna have 1 minus q squared over b squared. Then you realize that this will be looking similar. These two will be looking similar, so you realize that you'll be dealing with an ellipse as well. So same applies to letting your your x being equals to a constant r. Then you realize that you're gonna obtain the same version of a formula, so you realize that you'll be having an ellipse as well. That's why we are saying this type of surface is called an ellipsoid, right? Graphically in three-dimensional space where we have our coordinate system there. So this is your z, this is your x, this is your y. You realize that all traces, whether it is vertical or horizontal, is just an ellipse, right? So you realize that all those particular traces there is just the family of ellipses, right? Going down there, even in the vertical direction, right? This is how this thing works. So you need to understand that there's a special case of this particular ellipsoid, which is a sphere. Now there's some condition that you need to note here. You need to understand that it is a sphere only if your A is equals to B is equals to C, meaning this constants there, this ones here, must be equal for this to be a sphere. If only two of them are equal but the other one is not equal to these two, then it is not a sphere. For it to be a sphere, all these three must be equal. This is very important to note, right? Now I hope I gave you a good understanding of how ellipses are, how ellipses work basically, sorry for that, and how to identify them given an equation, right? Let's move on to hyperboloid of one sheet. So now we are looking at very interesting surface here, which is just a hyperboloid of one sheet. So you need to understand that the standard form of it, the standard form of it is given as x squared over a squared plus y squared over b squared minus z squared over c squared equals to 1, right? And there are a couple of things that you need to note here. The vertical traces are giving me a hyperbola, and the horizontal traces are just giving me an ellipse, right? Let's talk about it. Let's talk about it. What's going? Okay, let's talk about it. Let's talk about it. Let's talk about it. Let's talk about it. In the plane z equals to p, which is a constant, we obtain an ellipse. Is it true? Now let's check. X squared over a squared plus y squared over b squared minus p squared over c squared is equals to 1, right? X squared over a squared plus y squared over b squared is equals to 1 plus p squared over c squared. You realize that this is an ellipse, right? You know that this are the terms on the left and this is just a constant on the right there. So this is how this thing works. So you need to understand again that the trace, right, in the vertical axis, right, is your hyperbola, the vertical trace basically. So the vertical trace here is an hyperbola, right? Is it true that this is a hyperbola? Let's check it. So you realize that when you are letting your y to be a constant, right? When you're letting y to be some constant, you realize that you're gonna obtain something like this, right? You're gonna obtain something like this, which is a standard form of a hyperbola. Remember from conic sections, right? You did a lot of this, so I'm not expecting anyone to be struggling with identifying surfaces here, or you may say conic sections in this particular case. So again, if we check again in the plane x equals to r, right, is gonna be a what? A hyperbola again, because it's the same idea, right? It's the same recipe, the same concept, right? you'll realize that when you let your x to be r, you'll obtain a what? A hyperbola here, because you'll be having y squared over b squared minus z squared over c squared is equals to 1 minus r squared over a squared, right? This is just a basic idea. There's something important here that I want to bring your attention to, right? In this particular equation, you need to understand that the variable next to the negative number, right? The variable next to the negative number is an indication of the axis of symmetry. In other words, how our surfaces is symmetric, right? Actually, it is symmetric about that particular axis, right? So you need to understand that in the equation for this surface, two of the variables have a positive coefficient, we saw that, and one has a negative coefficient, right? And we say that the axis of the surface correspond to the variable with the negative coefficient. So our surface is symmetric about that particular variable with a negative coefficient. So it is very clear that this particular surface is symmetric about the z-axis. Why z-axis? Because the z-axis is that variable that is next to a negative sign. That's the reason why we are saying our what? Our surface is symmetric about what? The z-axis. I hope I'm clear there. Right? So let's get going. So I want to shift your attention from hyperboloid of one sheet and just bring you to hyperboloid of two sheet, right? And make sure you get the difference there. So you need to understand that hyperboloid of two sheet, it is given by this particular standard here, which is saying that z squared over c squared equals to x squared over a squared. Not equals to, sorry for that. Z squared over c squared minus x squared over a squared minus y squared over b squared is equals to 1, right? Or it can be x squared over a squared minus z squared over c squared minus y squared over b squared, right? Is equals to 1, right? Or it can either be y squared over b squared minus x squared over a squared minus z squared over c squared is equals to 1. These variables, they can either change signs, right? I'll talk the importance of the signs as we move along. So you need to understand that the trace there in the plane z equals to p, which is just your horizontal trace, is just giving us an ellipse, right? Or an empty set where there is no trace, right? This is something that you need to take note of, because I've been talking a lot about horizontal trace. I hope now you get what it means, right? Because here now, as we are letting y to be some constant, it can either be this particular constant or this one, it doesn't matter. You realize that you can get a family of ellipses, going down like this, right? Depending on the constant that you are choosing in this case. And you realize that when we are doing the vertical trace, where now your y is equals to q, which is a constant in this case, you'll realize that you'll be getting a family of hyperbolas, right? You realize that hyperbolas, they're gonna be a whole bunch of hyperbolas here on this particular surface, right? And you realize that even when you are letting your x to be some constant, you realize that you're gonna get a whole bunch of hyperbolas, right? And there's something that I want to point out here. You need to understand that in hyperboloid of two sheet, you're basically having a variable that is actually with the positive sign is the one that indicates the axis of symmetry, is the one in which the surface is symmetric about, right? I hope it's clear, that one. So let me just stress my point clearly here. They say in the equation for this surface, two of the variables have the negative coefficients and one has a positive coefficient, right? The axis of the surface correspond to the variable, this is very important, with the positive coefficient. The surface does not intersect the coordinate plane perpendicular to the axis, right? This is your two-dimensional space, and you realize that since we have a whole bunch of ellipses and a whole bunch of hyperbolas, you realize that since here is an empty set, you realize that our hyperboloid of two sheets does not pass through the origin. You realize that it starts at a particular point there going down and at a particular point there going up in the z-axis, right? You realize that the surface on its own is like sort of a bowel, right? Two bowels pointing in different directions, right? So it's very, very key that you understand the difference between your hyperboloid of one sheet and a hyperboloid of what? Of two sheets there. I hope I'm making sense there. So let's shift our attention to surfaces again, but this time the surfaces that we'll be looking at are surfaces where there is no a constant there, so, right? So we'll be dealing with surfaces where they're just variables, right? I'm saying a constant maybe on the right, on the left hand side, right? I'm not talking about this ones here. I'm talking either a constant on the left or the right. Right. Let's start with this one, the elliptic cone, right? So you need to understand that when we start doing our trace in the plane z equals to p there, z equals to p, right? Z equals to some constant p here there. You realize that you're gonna get a family of ellipses, right? The same idea applies when we let y to be some constant, right? In this particular plane here, you realize that you're gonna get a family of what? Of ellipses there. Even the same thing when you in the plane x equals to some r, you realize that you're gonna get a family of what? Of hyperbolas, sorry. So you need to be very careful there. You need to understand that in the xz plane, you realize that a pair of lines that there's a pair of lines, right, that intersect at the origin. Xz, pair of lines intersecting at this origin. YZ, pair of lines intersecting here, right? I hope I'm clear there. So you need to understand that the axis of symmetry in this case here is gonna be the variable, right, that has a negative sign, or you may say a variable that is on the right, or that is alone on the side of an equals to. For example, what am I saying? I'm saying that a variable that is on the left side of an equal sign, but it is alone there, right? This is something that you need to take. This variable here, z, is going to be your axis of symmetry, right? I don't want to say on the left because sometimes they can put it like this, right? That's why I'm saying a variable that is alone, that is isolated, right, next to an equal sign, is the one that is the axis of symmetry, right? So let me just stress my point there. The axis of the surface correspond to the variable with the negative coefficient, okay? The traces in the coordinate planes parallel to the axis are intersecting, right? This is a very, very important point to note. Very, very important point. This is what I was stressing there. So let's talk a little bit about elliptic paraboloid and try to understand, right? We need to understand that elliptic paraboloid has this standard. This is called a standard form of it. This is a standard form. This is a standard form of an elliptic paraboloid, right? So you need to understand that elliptic paraboloid, when you do a trace in z equals to p, right? Z equals to p, where z is equals to some constant there, you realize that you're gonna get a family of ellipses here as well, right? Going down like that. But now there's something interesting here. You realize that when you are doing a trace in a vertical trace there, you realize that you're gonna get a whole bunch of parabolas, right? Parabolas, as well as the x equals to some constant parabolas, right? In the plane, here is gonna be in the plane xz. Here's gonna be in the plane yz. You need to be careful. This is going to be in a plane xy, right? These are some of the things that you need to take note of. The x's correspond to the linear variable. In other words, the variable that doesn't have an exponent there, right? This is basically what it means. A variable that is isolated and it doesn't have a what? An exponent. A variable of first degree, right? Of first degree there. This is very crucial to understand. I hope it's clear, this one, right? And the orientation of this is going to be based on the sign of your z, right? This is going to be based on that, whether it's looking this side, sorry about that, whether it's going to be like this or it's going to point up as indicated in the picture. It's going to depend on the sign of z, right? Let's talk again about this special quadric surface. It's called the hyperbolic paraboloid. So basic idea is that when we look at traces again, which is a very fundamental aspect here, we'll realize that when we do a trace in the horizontal, in the z, basically in the z axis, you realize that you're gonna get a hyperbola, right? And the hyperbola that we're gonna actually get a family of hyperbolas, right? Same applies to letting your y equals to some constants. You're gonna realize that you're gonna get a whole bunch of ellipses, right? So here we'll be dealing with the xy plane. Here we'll be dealing with the xz. Here we'll be dealing with the yz here, and you realize something interesting here. You realize that this family of graphs, this family of conic sections here, they're the reasons why this particular surface looks like this. The reason why this particular surface looks like this. So you will realize that when your z is equal to some constant, you realize that you're going to obtain a whole bunch of what do you call this, hyperbolas, and you realize that constant p is just a constant that varies with the plane there, right? And y, when your y is equals to q, you realize that you'll be having y, where's y, this is y here, and y is equals to some q, which is just varies as well. So you realize that you're gonna obtain a whole bunch of parabolas here that open. If we check here, let's check where they open those parabolas. Z equals to y must be equal, so they open upwards, right? They open upwards, so you're gonna be having this is just a constant that indicates a shift of this particular parabola. It is shifted downwards, so you realize that that's why this thing is below the positive z, the what do you call those things, those parabolas. So you realize that you're gonna get a whole bunch of parabolas there, and you realize that even when you let your z to be some constant number in the plane z, I mean x equals to r, you realize that you're gonna get again a whole bunch of parabolas there. So you need to again remember that the axis of the surface correspond to a linear variable, the variable that is isolated, right? You realize the difference between these two. You realize that for a hyperbolic paraboloid, right, if you check a hyperbolic paraboloid and if you check elliptic paraboloid, the only difference is the sign, right? Be very careful with the sign there. Be very careful. Here you have a plus, here you have a minus, because uh, when you understand, and again you understand the idea of traces, you won't get your equations mixed up, right? Make sure you understand the fundamental idea of traces, because traces are very key there. Even though you get mixed up with the equations, but if you know the traces and how to put them graphically, how to put them on a paper and try to make sense of them, then you'll be fine with this kind of aspect of quadric surfaces. I thank you so much. We'll meet in the next video where we will attempt a few questions based on these ideas. Thank you so much.